If a car accelerates down a straight highway, what does the speedometer actually tell you at the exact instant of 1 second? In basic algebra, calculating speed requires two separate points in time, the distance traveled divided by the elapsed time. But at an exact frozen instant, no time has passed. Zero distance divided by zero time is completely undefined. This single question is the historical origin of differential calculus. To see how mathematics solves this problem, let's look at a coordinate graph of motion. Suppose the position of our car is described by the simple curve s of t equals t squared, where t is time in seconds and s is distance in meters. At 1 second, the car is at 1 meter. At 3 seconds, it has reached 9 meters. If we calculate the average speed over this entire 2-second window, we divide the change in position by the change in time. 9 minus 1 divided by 3 minus 1. This gives an average speed of 4 meters per second. Geometrically, this average rate is the slope of the secant line connecting our two data points. Now, how do we find the speed at the exact moment t equals 1? We shrink the observation window. If we measure between 1 second and 2 seconds, the average speed drops to 2 meters per second. If we narrow the window further between 1 and 1.01 seconds, it sharpens to 2.01 seconds. Watch what happens on our graph. As the time increment delta t approaches 0, the second point slides down the curve towards the first. The secant line rotates, and in the limit, it locks into a single tangent line that grazes the curve at 1, 1. The slope of this tangent line is exactly 2 meters per second. This is the central insight of differential calculus. An instantaneous rate of change is the limiting value of average rates over vanishingly small intervals. In our next lesson, we will see how mathematics formalizes this secant rotation into the derivative function.